Okay, so this is our final video on matrix multiplication. In the previous video, we explored um, essentially the definition. We explored how to compute a matrix product, how to do A times B, and we saw that the general algorithm is you follow this row times column mantra. Rows from the left times columns from the right. You essentially form these dot products, and you take each of those dot products and set them as the entries for a new matrix, which we call the product. So the definition, if you want to write down a formal definition, is given as follows. So we want to form a product A times B. So as we saw in the previous video, if I want to do A times B, then the numbers of entries in the row, each row of A, has to match the number of entries in each column of B. So these two numbers have to match, okay? N and N, they have to match. The numbers on the outside, the M and the P, they tell you what the size of the product will be, right? So checking that those numbers match on the inside makes sure that the product is defined in the first place. The numbers on the outside will tell you the size of what that product should be. Now, once you know what the size of the product is, you need to compute the entries within, right? It's supposed to be a matrix, so what are the entries of that matrix? So the entry that goes in row I and column J is you take row I from A and you multiply by column J from B, right? So for row I, column J, it's row I times column J, but the row I comes from the matrix on the left, the column J comes from the matrix on the right. So if you want to, you can, if you want to kind of write everything down in terms of index notation, if we want to say, well, the product A times B is going to be an M by P matrix with entries Cij, where the formula for each entry Cij is given by an expression that looks like this, right? So notice that the index I for the A's tells you that you're in row I from the matrix A. The J here for the B's tells you that you're in column J for the matrix B. So that's the definition. Rather than trying to kind of remember this formula, which admittedly is a little bit intimidating with all the I's and J's and the numbers and the A's and the B's and and if you want to make it really scary, you can use summation notation. Don't worry if you never dealt with summation notation, it's not something that you need in this course, but it certainly allows you to clean things up if you are familiar with it. Here's a nice schematic. This is I didn't make this myself. I borrowed this from a website called TixZ examples. So this TixZ is a package for producing diagrams in documents like this, and so somebody came up with this one. So here's a way of visualizing matrix multiplication. When you want to do the product A times B, arrange them like I did in the last video. Put the matrix A on the left, put it over here. Your matrix B goes on the right, but you shift it up. You put it up and to the right. You put it over here, right? And then you align the rows of A with the columns of B, and that tells you what the entries in your new matrix should be. So each entry here in one of the rows has a corresponding entry in each one of the columns, and we multiply these together. So we do the A's times the B's, A21 times B12, A22 times B22, and so on. We form all those products, we add them all up, and that gives us the entry. So this schematic, I think, gives us a nice way of visualizing matrix multiplication. Okay, so let's do one more example just to make sure we've got the hang of things. Here are two matrices, A and B. Let's compute the product. So if I want to do A times B, right, then for A times B I should do this. So I put my matrix A on the left, 2, minus 3, 1, minus 4, 0, 3. So there's A. B goes on the right, but I slide it up. Minus 1, 7, 3, minus 4, 2, 0. Okay? So we've got 2 rows on the left, we've got 2 columns on the right, and the product has 2 rows, 2 columns, as it should. I'm doing a 2 by 3 matrix times a 3 by 2 matrix. The 3 matches with the 3, so we know the product is defined, and the 2's on the outside tell us that the outcome should be 2 by 2, right? So if we do row 1 times column 1, so row 1 from A times column 1 from B, we've got 2 times minus 1 plus minus 3 times 3 plus 1 times 2, right? So we're doing 2 times minus 1 minus 3 times 3, 1 times 2. We're doing those 3 products. We're adding them all up, so we get minus 2 minus 9 plus 2. We get a minus 9 going in there. Row 1, column 2. So row 1 from A times column 2 from B. So we're going to do 2 times 7 minus 3 times minus 4, 1 times 0. Okay, so that's going to be 14 plus 12 plus 0 gives me 26. And then I can do row 2, column 1. Right, so I'm doing now entries from row 2 times the corresponding entries in column 1. So I do those 3 products there. Minus 4 times minus 1 plus 0 times 3 plus 3 times 2. So 4 plus 6, I get a 10. And row 2, column 2, same story. Minus 4 times 7 plus 0 times minus 4 plus 3 times 0 leaves me with minus 28. Okay, so that gives me AB. So AB is this matrix, minus 9, 26, 10, minus 28. That's my AB. Okay, what about doing BA? Okay, if I wanted to B times A, then I put my matrix B on the left, minus 1, 7, 3, minus 4, 2, 0. I put my matrix A on the right and I slide it up, 2, minus 3, 1, minus 4, 0, 3. And as before, we kind of line things up. We see that the outcome should be 3 by 3, 3 rows on the left, 3 columns on the right. That agrees with our definition. And we go about computing the row times column product. So this time I think I won't bother to write it all out. I'll just kind of work through it. So we do for first row times first column, minus 1 times 2, 7 times minus 4. So minus 2 minus 28, I get minus 30. Minus 1 times minus 3, 7 times 0, so I get a 3. Minus 1 times 1, 7 times 3, so 21 minus 1, 20. Row 2 times each of the columns, 3 times 2, minus 4 times minus 4, so 6 plus 16, that gives me 22. 3 times minus 3, minus 4 times 0, so that gives me minus 9. 3 times 1, minus 4 times 3, so 3 minus 12, minus 9. And then for the final row, 2 times 2, 0 times minus 4, 2 times 2 gives me 4, 2 times minus 3 gives me 6, 2 times 1 is 2, right? I didn't worry about what was in the second row there because those guys are getting multiplied by 0. So that gives me B times A. Right? Minus 30, 3, 20, 22, minus 9, minus 9, 4, minus 6, 2. Okay. And again, one of the things you should take away from this is that B times A is decidedly not the same thing as A times B, right? They're not even the same size, let alone do they have the same entries. And you may be wondering, what if I came up with an example where AB and BA did have the same size? Would it be true then? And the answer is still no. It's quite rare, in fact, for matrices that A times B equals B times A. In almost all cases, the order actually matters. So the order in which you multiply matrices matters. And so this is something that we don't encounter with numbers, real or complex. You know, most of the multiplications that we've seen so far in our lives are ones where A times B is always the same thing as B times A. But for matrices, this is just not true. And maybe one way to think about why it's not true, if you think about the example in the very first video, I mentioned that you can kind of think of each matrix as defining some sort of function associating one set of variables with another set of variables. And multiplying matrices, it turns out that multiplying matrices is kind of like composing functions. And you might remember from high school that the order in which you compose functions matters, right? F composed with G, F of G of X is not always the same thing as G of F of X. You probably saw some examples like that. And so if you think of matrix multiplication as related to function composition, then the fact that A times B is not equal to B times A might make a little bit more sense. Okay, so that property is out the window. We don't have commutativity for multiplication, but we do have some other properties. So it is distributive. And by the way, because A times B is not equal to B times A, I actually have to give two distributive properties, right? One for multiplication on the left and another one for multiplication on the right, because multiplying on the left is not the same thing as multiplying on the right, because A times B is not the same thing as B times A. So two different distributive properties. I have an additional property saying that if I have a scalar inside of a matrix product, I can move that scalar around. I can pair that scalar with B, I could pair it with A, I can put it here, I can put it here, or I could bring it right out front. I could do the matrix multiplication and then do the scalar multiplication. And so although matrix multiplication is not commutative, it is associative. If you want to multiply 3 or more matrices, as long as the sizes match up, right? So those have to be the same and these have to be the same, right? As long as those guys match up, then I can do A times B times C, and it doesn't matter whether I first do B times C and then multiply by A, or whether I do A times B and then multiply by C. And by the way, this one really is necessary here, right? With addition, you can mentally do addition of 3 or more things without having to group things together. You can kind of add 3 things at a time. If you're doing matrix multiplication, this is really a necessary step. If I want to multiply 3 matrices together, I have to choose to group them one way or the other and do one multiplication followed by another. There's no natural way of doing all 3 multiplications at once. You really have to do one pair at a time. You've got to break it up like that. Okay. So, almost done. One last thing to note is there are a couple of matrices that pop up that are of worth mentioning. One is the zero matrix. We've seen the zero matrix before, right? The zero matrix. So there's one for each size. So this is just the matrix with all zeros. Right? And we already know that the matrix, the zero matrix, acts as the additive identity for matrix addition. But it's also true that if I take the m by n zero matrix and I multiply by any other matrix, say n by k, right? Multiplication by 0 gives me 0. But notice that the size might vary. If I take an n by k matrix and I multiply by the m by n zero matrix, I get a zero matrix, but it's of size m by k. It would also be true that if I took say, if B was an m by n matrix and I multiply by, actually it's, maybe B is size, let's say P by Q, and I want to multiply by a zero matrix, then that zero matrix, well, it's going to have the right size, so it's going to have a Q there, Q by R, let's say. That also will give me the zero matrix, but it's going to be a zero matrix of size P by R. Okay. Now, the identity matrix. So the identity matrix, what you're looking for here is you're looking for a matrix, say IN, and it's always going to be a square matrix, and you want you're looking for something that acts like 1 with respect to multiplication, right? So you would want A, if A is, say, m by n, and you multiply by the n by n identity matrix, you want to get back A, and if you multiply on the other side, well, you've got to adjust the size. It's going to have to be m by m times A, m by n. That nothing should happen. So you're looking for a matrix where multiplying by that matrix does nothing. It turns out you might think your first guess might be to take a matrix consisting of all ones, right, since the zero matrix consists of all zeros. But if you think about the way, because when you do matrix multiplication, you are adding when you form those dot products, right? If you put everything equal to 1, you would just be adding up all the entries in each column, and you wouldn't have this property. So what you actually want is you want ones just down what's called the diagonal. So you want ones down the diagonal, and you want zeros everywhere else. 0, 0, 0, 0, 0. So that's what the identity matrix looks like. Ones down this this so-called main diagonal, like so, and zeros everywhere off of that diagonal. That's the identity matrix. And you can check that it satisfies these properties. Okay, that's it for matrix multiplication.